All right, so we're in our last kind of content lecture of the semester. Since we finished up pointers so quickly, I thought I'd also illustrate the classic stack smashing attack today, if we have time. But first, I want to go over the homework, go over, bless you, any questions you might have. We'll have a review for the final on Monday. By then, you'll get all the content, but just like for the midterm, it'll be based on the homeworks, the programming assignments, and the lecture content. Just as a reminder, it'll be about 50% larger than the midterm, so you'll have 50% more time. I did put an announcement that the exam will be at 8:05 instead of 7 a.m., so that'll give us an hour and 45 minutes to do everything for the final. It also means you have 50% more notes you can bring, so it'll be 12 pages. 12 double-sided pages, so that's 24 total. So I have no real control over the time or the place of the exam. It'll be here, but this is the time we were allotted, so I'll just move it an hour later. Questions on It's cumulative. So it says here that it'll be cumulative. Final is cumulative, but proportionally more second half material. Yeah. Oh, sorry about that. Sorry. Yes, I was supposed to be sharing my screen. Yeah, the downside of not being able to actually see the screen from here. So final's cumulative. As the syllabus points out, you have 12 pages double-sided, so 24 single-side pages. Well, bring 12 pages maximum. And I've moved the exam to be a little later with the same end time. So what's that? I didn't. I haven't set it up yet. Keep reminding me. You can put it on EdStem, but I need to just go in and set the time and stuff for the final. Just let me know if there's an issue. You can always reach out to yourself as well, and CC me, and I'll just confirm it for you. Let me make a reminder to do that. Oh, I made a reminder to update the time, but I didn't make a reminder to update SAS. Okay. All right, any other questions on logistics for the end of the semester? And so, it's always this is the project deadline for everything, including all resubmissions. It's 4/28, so that'll be all the grading will be done 4/29. Any questions on logistics, end of semester stuff? If you need to do a makeup exam, send me a message on EdStem, private message, telling me, give me the reason. Should be like sort of reason that UCF accepts, and all of the times you're available for makeup. I'm going to try to do one makeup exam. I have to rewrite the exam, so I'll do one makeup exam, ideally. All right, questions on pointers or any of the material we've been covering for the last several weeks? Everybody good on pointers? We got through it faster than I thought we would. It took 2 lectures to do it. And I got the video up as early as I could Monday. Other questions on pointers? Everybody's good on pointers? All right. Great. Any other questions on CoGen? Are they the CoGen assignments? Since I think CoGen 2 is still pending. That's going to be due today. But remember, you can always resubmit up to the final project deadline. All right, let's do the homework. So if a variable t has offset -40 from the base pointer, write x86 assembly code that will retrieve the value of t1, store it in RAX, then, this doesn't make sense. Then store 11 to the memory address. Then store 11 to the memory address held by RAX. Yes, this makes sense. Okay, so quick quiz. What simple IR operation does this correspond to? So it says take the value of T1 and then store 11 into the address held by RAX. So what simple IR instruction does this correspond to? So in assembly, you would store the address like this. Well, let me just do let's do the assembly first. So how would this x86, 64 assembly, what would that look like? Okay, so you take the offset of 40 from RBP, take that address, and load from that address the value into RAX. So that's what this first clause is saying. So T1 has an offset of negative 40. That's how we store addresses for function local variables. We take the value of that function local variable and copy it to RAX. And then how do we store 11 into the memory address held by RAX? Yeah. Okay, put what in parentheses? Okay, so this is how we'll store into the address held by RAX. What about the rest of this instruction? Yeah. Go ahead. Somebody. Go ahead. Say again? Well, you can use move for that. You don't need to add. I mean, I guess, yeah, you don't need to do add. You can move 11 into the address held in RAX. That's what the parentheses denote in AT&T syntax for x86 64. Okay, so this is the answer. What simple IR operation does this correspond to? So T1 is involved in here somewhere, 11 is involved in here somewhere, and there's an assignment somewhere. Yeah. Okay, so let's see. So star T1 equals 11. So for this assembly instruction, does T1 change? Does T1's value change? So I copy T1's value into RAX. Do I ever store to T1's value? No, I never store to it. So T1 doesn't change here. So how could it be that we're assigning? Are we assigning to T1 here? Let's say T1 was assigned to be the address of X. What variable changes with this move instruction? What variable gets updated to 11? X, right? Because T1 is holding the address of X. This denotes the address of T1 and loading its value. So now the value of T1 is held in RAX. So now RAX holds T1's value. What is T1's value? T1's value is the address of X. Then when I move, I'm not moving into RAX. I'm not moving into T1's address. I'm moving into whatever address RAX has. Because T1's value is the address of X, this is updating X. This is actually updating X's value. Whatever memory location given by T1's value. So yeah, this corresponds to the dereference assignment, this sequence of instructions, or it's equivalent to it. Questions on this? Does this make sense, kind of? Can't tell if you're totally stunned or you totally get it. This is boring. Everyone's very silent. Any questions, other questions on this? Yeah.
What does the parentheses mean?
The parentheses just indicates, it's called, I think it's called memory indirect addressing. So if you just say move 11 to RAX, does this change memory? No, because RAX is just a register. RAX is a register. This is just a register copy. So this, after this, the register RAX holds 11. What if I say move 11 into, I think you would just do it something, you would just do some, memory address. Does this involve memory? I didn't show this before, but yes, this loads 11 into the address given here. So if we want to use pointers, if we want to do something like pointers where we don't know the actual address at compile time, we want to have, say, the user or user take a reference or have the user give us an address. The way that we can have a pointer-like register is by putting parentheses. The parentheses say, don't store this value into RAX, but store it into the memory location that RAX holds. This is just treating RAX as a pointer. This is the same thing as saying something like RAX equals 11. And same thing when the parenthesized register is a source. So if I say move RAX into RBX, this is in C like saying this, RBX equals star RAX. So you can, if you don't understand, if pointers in C are already confusing, it may not help to say, well, okay, this is like a star in C. That is basically what it's like. But the kind of physical machine way to think of this is that this is a load. This one is a load operation. This is a load where the address is given in a register. So this is what's maybe a little confusing about the Intel world or the x86 world, is that the move instruction is very overloaded. It means register copy, it means immediate copy, it means load, it means store. It means lots and lots of different variations. So if you were doing MIPS, you'd have I think you have separate instructions for like register copy and for memory load and store. But in the Intel world, they're all given the same mnemonic, even though they are different opcodes. There are different actually operations in the machine. And so it's the syntax of the arguments that denotes which kind of operation this is, whether it's a memory load, memory store, memory indirects load or store, immediate load, immediate store. Not immediate store, immediate load, register copy. Does that answer your question? Yes. Other questions on this? And so it's important to understand this, C or simple IR semantics and the assembly semantics, so that you can write a compiler that will translate between the two and have an equivalent program as the output program. Yeah?
Do you think of the parentheses as basically processing whatever is the value in that variable as an address?
Yeah, that's exactly it. So this says treat the register value as an address and do a load from it, a load or a store to or from or to it. All right, any other questions on pointers? So it's helpful to think about it in this extremely meticulous, detailed way when you're doing debugging. Because writing a compiler is hard enough, getting equivalent code, but you actually have to demonstrate to yourself that the code is equivalent. And if you have a bug, you have to be able to step through the output code to be able to see what the bug is and then trace it back to your program to figure out what caused it. All right, everybody good on pointers? 100% on CodeGen 3? No problems with CodeGen 3? Okay, maybe not that extreme, but. All right, so, we still have several weeks, we still have office hours. They're still at STEM, so please ask questions. As I said before, I'll try to grade CodeGen 3 before the deadline. Just keep telling me on EdSTEM, and I'll do a mass grade so that you can get some feedback, and have an opportunity to resubmit. Yeah. Oh, that's right. Yeah, I haven't done office hours for. I haven't done office hours yet. I assume I'll probably just keep them to be the same times, Monday and Wednesday. Let me know on EdSTEM if that doesn't work for you. So I'll post an announcement. Let me make a to-do for myself. Announce end of semester office hours. So if I just do Monday, Wednesday, keep that going. This is a Monday, right? This is a Monday. So the project will be due on a Monday, and then I'll just have the same office hours that day. And that's when you can come, complain about your grade or fight for your grade, get feedback on the project. I'll probably just keep Monday, Wednesday. I think that should do it. But remember, EdSTEM is there. Let me know if you need other times to meet. All right, other questions? Okay, let's do attendance. Okay, so let's go over stack smashing attacks. And this is probably one of the most famous and early exploitation of software, particularly C software. And to understand it and see how it's exploited, you have to understand how compilers work, how functions are implemented, how the stack works is maintained by the compiler. So having this knowledge of how the compiler works, how the operating system works, how the stack is used to store local variables, this knowledge was exploited in order to run arbitrary code from other people's programs. This is kind of one of the early examples of memory corruption attacks that have become the dominant form of exploitation, publicly known exploitation of software. Okay, so let me give you a brief overview of how this is going to work. So I think everyone, hopefully by now, remembers the stack. So let's say I call some function f. What does the stack frame for f contain? Yeah. Okay, so if there's any stack allocated parameters, those will be there as well. But there'll be the return address and what operation that we used in class in the x86 architecture, what puts the return address in the stack? How does it get there? Yeah. What's that? Well, what instruction? The offset's not an instruction. What assembly instruction puts the return address on the stack? You could use push. What about the one we saw in class? Or what do you do after? How do you make a function call in the assembly world? Call, right? Call. Call does two things. It pushes the return address. The return address is just the next program counter, the next instruction after the call instruction, and then it branches to F. So that's how the return address gets there. And then the next slot in the stack frame is the old base pointer. How does that get into the stack? Is it the caller or the callee? What's that? Oh, yeah. Callee, yeah, the callee. In the prologue, one of the first things you do is call push RBP. That's how the old RBP gets on the stack. And then we have our local variables. So the way the stack smashing attack works, which is what I alluded to, I've alluded to this several times, is say we've got an array. Say we allocated an array that has 1, 2, 3, 4 slots. Now, I didn't really talk about arrays very much, but if we have an array, it just allocates a slot on the stack effectively for each element of that array. That's how you can think of an array working, right? Array is just a continuous sequence of memory addresses. I think you probably learned this in CS1, right? What arrays are. So if I have a single variable, like b, well, that'll, in our compiler, that just takes up one slot, one 64-bit slot. If you have other types of numbers, like 32-bit and 8-bit numbers, this can get a little more complicated for efficiency reasons, but let's just assume that each variable is given its own slot on the stack. And if we have an array, we just have a slot, a statically allocated array. We have a slot for each element of that array on the stack. Does that kind of make sense? This is how you probably all learned arrays. You learned arrays as like a sequence of boxes, right? And they're base 0. So if this is array A, then we've got 4 slots in memory for it, and they're indexed starting from 0. Why are they indexed starting from 0? Why do we have to learn to count from 0 in C? Yeah. It doesn't really have anything to do with binary. Yeah. Well, yeah, you're getting close to the base address. It's because if you look at the Intel, look at this instruction that we used for getting an offset from RBP. What did we do? We said, give us the value, load from the address given by RBP, and then we put an offset here. So we said something like -40. Well, if we say -0 offset or +0 offset, what does that mean? You just add 0 to RBP, which is just RBP, right? The way arrays are laid out in memory and addressed is the same way. The first, if we have an array like this, the first element is just the address of A. So if I have an array and I just take, I can't write, oh my god, I forgot how to write an ampersand. Oh, I can't write an ampersand anymore. Oh, okay, that's how I had to look on my keyboard to write an ampersand. So if I take the address of A, I mean A is an address, but in C it's already a pointer. But if I took the address of A, if it wasn't an array, well, I would get the address of the memory location in the stack, right? So the way an array works is it's just a pointer to the first element in the array. So A is a pointer to this element in memory. And so if I want to access an element, I just add the offset to the A's address. So if I add offset 0, I just get the address that A is already pointing to. So this is +0 from A. This is +1 times the width of the the data type. But you see how this works? So +0 is just the address that A is pointing to already.
Will it always be the end of the array?
It'll always be the beginning. This is how C lays out memory. So it's +0 times the bit width. So if the bit width is 8, or the byte width is 8, then each of these is just times 8. And so it works just like RBP works. You can think of RBP, the base pointer, as an array. It's an array that contains all of the local variables of the function. Now for RBP offset 0 is the old base pointer. For an array, the first element is you can store data in it. It's not some other underlying information. It's just you have an array of 4 elements. Offset 0 is just the address that A is already pointing to. So A is a pointer, it points here. Index +0 is just adding 0 to that address, which gives you the address that A points to. Adding 1 times the byte width, gives you the next slot. Adding 2 times the byte width gives you the next slot, and so on. So this is like +8, +16, +24, and this is +0. That's why in C, arrays are indexed 0, because it's a very literal translation to to many assembly language operations. And the Intel world even has some special syntax for doing what is basically an array index. So this memory addressing mode is basically array index addressing. Anyway, okay, so that's how arrays are laid out in memory in the C world. And how are strings represented? Does C have a string data type? No, right? How do you, if you want to have strings in C, you want to be able to write hello world. Yeah, how do you do it? It's an array of characters, right? It's an array of characters. That's all a string is. It's an array, right? So if A is a string, what's the data? It's an array of characters, so the data type is character. Now, characters are only 8 bits, but let's just pretend we have 64-bit characters here. So if I, I'll just put my name here. If I want to store a string, Paul, if I'm in C and I say something like A4 equals Paul, I can't remember if this is the exact right syntax, but something like this. You might have to remove the 4. Then this is how the string is going to be laid out in memory. Is this a surprise to anyone? Has anyone not seen this? How strings are laid out in memory? Have you seen this in CS1? Okay, I think everyone should have seen this in CS1. So this is how it's laid out in memory. Why am I going up the stack? Why am I going down the stack here? Why is it going up in my diagram?
I would think it just gets set from RBP, so it starts at the end and adjusts the English interface between the end of the array.
Yeah, you're circling around the right point here. So if this is the address of A, RBP points here. How does the stack, in terms of the memory addresses, when I call a new function, is that function going to be in a lower addresses or higher addresses? When I push a new function stack frame. Lower, right? So whenever I access stuff on the stack frame, I did a negative offset from RBP. If I push a new function, it's going to be here. It's going to be even more negative. But what about arrays? Are arrays negative or positive? They're positive, right? So RBP, or my function allocates A to start here, and then any string that I copy there, or any string that I put in there, well, those are going to be positive offsets from A. This is going to be +0, +1, +2, +3, in terms of array accesses. Questions on this? Does this make sense? Questions? Hopefully this is like basic C stuff, or maybe stuff they didn't think was relevant at the time. But for clever attackers, this is a highly relevant thing. Because what happens if I say access array element? Okay, here's a common mistake that people do. Okay, so this is not correct syntax here. So it would be something like this to initialize a pointer. But what would happen if I accessed array element 4 and I set it to be, let's say X? What's going to change here in memory if I do A4 equals X? That should not be a string. That should be a character. How is my memory going to change when I assign index 4 to X? Yes, the old base pointer is going to be overwritten with X. It's going to differ a little because these are not 64-bit values, but I'm going to start corrupting this part, right? Because I've done an array index. I've done an array out of bounds, right? If I only allocated this to have 4 slots, well, array index 4 is actually element 5 of the array because we start at 0, right? Now, what if I do A6? Now, again, this is 8 bits. Let's pretend that this was 64-bit characters. If I did array element 6, if this was +4, this is +5, what am I going to be overwriting now? Well, if A4 overwrote, so let's not make this a character. I'm going to make this a 64-bit number, and just pretend that I'm have 64-bit characters. So if A4 is overwriting or corrupting RBP, what is A5 going to be overwriting? The return address, right? The return address. So this means that if I don't have any checks on array out of bounds accesses, writes, I could end up overwriting the return address of the function. Now, if you're doing string operations, that's probably not at all what you intend when you're doing string operations. You were probably just hoping to access other elements of the string. But because of how memory is laid out by the compiler, you can actually be overwriting the return address, or as your colleague pointed out, maybe even overwriting other parts of the calling function, the calling function's local variables, or the calling function's return address. That kind of makes sense? So this is called stack smashing. This is where you write outside the bounds of arrays, which is undefined behavior in C. It's on the user to not allow that to happen. And because most compilers will just compile undefined behavior anyway into the simplest thing that it can do, which is to just pretend that it's an infinite bound array, it will actually translate these writes, even though they're not valid C, into memory stores that will actually overwrite the address. Now, and you can crash a program this way, right? So most likely, if you just do this with our arbitrary values, you'll eventually get some sort of seg fault or other sort of halt in the machine. But what a clever attacker can do is not just overwrite this address, but overwrite it with an address to code that they control. Now, how could they put code that they control into memory? So, the compiler turns it into binary code. That binary gets taken by the loader and put into memory. So how could the attacker ever add their own code into memory? Yeah.
Well, if there's any way to input something into the program, then you can input, something that can be read as code, and then somehow, if you can get the program counter to go to that part of memory where you put your code, then it'll start executing that code.
Exactly right. So the classic stack matching attack will not only overwrite the return address with some value, it'll actually overwrite other parts of the stack with code, pre-compiled, pre-assembled machine code. So if you're reading in strings from the user, which is an extremely common thing to do in C code, you're letting the attacker write into memory. So this could all be code. But how could they ever call it? How could they ever run it? Well, if you're allowing them to overwrite the return address, now you've given them control. You've given them a way to jump to their code. Because what happens after this function ends? It pops this value, whatever it is, doesn't care what it is, it pops this value and branches to it. That's what the return instruction does. So if the attacker can make sure that that address will jump somewhere into the data that they input to the program, voila, they can execute arbitrary code. Because remember, von Neumann architecture, code is data, data is code. It's all just binary values in memory. It doesn't matter, the machine doesn't care what it is. If it sees a binary code here and you've pointed the program counter, the instruction pointer, to that and told the process to start running it, it's going to run it. So often, if you do this accidentally, it'll be an invalid opcode and the hardware will stop. Or you'll branch to an address that doesn't have code, and yeah, same thing. Either an address that you don't have access to, and then the hardware will stop, or to code that it'll interpret the code, but it'll try to interpret it as a machine code opcode. And if it's an invalid opcode, the machine will say, hey, that's invalid. But you could specially craft your data to encode pre-compiled, pre-assembled instructions here. And the most popular thing to do is to write code that opens a shell. So say you're on a remote machine. So let's say I can, run arbitrary code. On your own machine, that's sort of pointless because you can already run arbitrary code on your own machine. But if I'm running a server here, say this is my web server, how does a web server work? You just send text. Probably don't have time to go into it, but you send text. You send an HTTP request. It's literally just text. It's kind of like a text chat between the server. And this text gets processed by a program on the server. It's just like, remember we talked about standard in and standard out? To the web server, there's no real distinction between input from the web versus input from the local machine. It's just input, and it gets processed very much the same way in the C program. So when you open a server to your machine, or you open it to the internet for anyone to send messages to, well, you're letting anyone give data to your programs on your machine. So if there is this vulnerability where you have string operations that allow inputs to overwrite the stack kind of to an arbitrary depth, well, now a remote attacker can start running arbitrary code on your machine. And then they basically own your machine. They can do whatever they want. So the most popular thing to do is to open a shell, just like we do on Eustace. So imagine you need authorization to go to Eustace, but imagine you could just send the code to open a shell. We learned what the syscalls look like, right? We have syscalls for loading a program. So if we could precompile the program that, or precompile a C program that will call the syscall exec, if we can just call this exec shell, if we can call this is just a syscall, we just translate this into binary, into a machine code. If we can somehow send this code to the server and modify the stack so it actually branches to this code, well, now on this socket we've already opened, we're running a shell. It's basically like logging into Eustace, but in a way that the sysadmin did not expect you to be able to do. They didn't expect you to open a shell and just run it. But a web server and a shell, a remote shell, in principle, they're the same thing. It's just a text communication between you and the server. It's just that the web server program doesn't allow you to run arbitrary programs. It has a restricted set of behavior, whereas the shell program allows you to also run arbitrary programs. Even worse, if that web server is running as root, well, now you are the super user. You are the admin of that server. Nowadays, web servers are not run as root anymore. Hopefully, don't run anything as root, honestly. But decades ago, people would just kind of root. You kind of need access. You need root to be able to do things like open ports for having a web server. So that's the crux of this stack smashing attack. And there's huge amounts of variation to this. I'm going to show you one today that I just took from a blog post where they use a different entry point to get code into the process. But this is the classic way to do it. Smash the stack, and in your string input, put precompiled code to run shell. And voila, you've got an open shell. Yeah.
I gotta send this to you on Edstone because I think you find it interesting. But one of my favorite examples of this I saw on YouTube recently is in the game Super Mario Bros. They use a glitch to get some arbitrary code executing, and then they write a small program that lets them reprogram the game through controller inputs. And this is all being done through what's called a TAS, Closed Speedrun. It's just
okay.
that are meant to be played back. So
it's like a programmatic input.
Yeah, it's too fast for a human to do, but it's like a programmatic.
Nice, send it. Yeah, put it on Edstone.
So they reprogram the game through the controller, and then they use that to run a program to play a video through the controller port, and it's a music video
that's a lot of data.
I guess you probably wouldn't know what it is, but I thought it was hilarious.
Put it on Edstone. Yeah, I'd love to see it. Yeah, that's very cool. So, I guess even controller inputs can trigger some memory corruption error. Yeah, and this is a risk. I mean, if anyone's interested, I'm sure a lot of people are interested in security. Join the Hack UCF club, by the way. It's just an ad for Hack UCF. Combating this and other exploits to software is a huge exercise. There are probably over 1 million jobs openings right now in security. Just as a little ad for security. I'm trying to remember the website. But practices to try to avoid having your machine, owned or taken control of by other people is basically a job these days. So this is the site cyberseek.org, which shows. I think it's this site. Yeah, it shows number of job openings. Oh, sorry, 500,000 job openings. A mere 500,000 job openings. Yeah, so there are job openings all over the place, all over the country. So basically anytime you put any device on the internet, whether that's your refrigerator or your home security camera or your home listening devices, anytime someone on the internet can access that, you've allowed them to access that, you open yourself up to exploitation if the software is exploitable. So then somebody can run whatever they want on that, which could include, say, copying recording data or terrorizing your children with weird audio, which has happened in the past. Yeah, question?
Not so much of a question, more of a comment of something. So for summer camp, I actually did a cybersecurity course, and essentially they had an entire example of why smart homes are very vulnerable to attacks. And my neighbor had just gotten these new light bulbs that were connected to the Wi-Fi.
Should I pause the audio? Is there something?
They told us, this specific model light bulb, so I just happened to mention my neighbor, hey, out of curiosity, what light bulb do you have? It was the exact same model, and I just consistently messed with his lighting colors.
Yeah, you may not want to admit that publicly, but probably harmless stuff, and he was acceptable to it. And he was,
I told him after the fact.
He knew,
Probably actually swapped out, because he thought it was his kids doing.
Yeah, so, and the IoT devices are not historically the best at security practices, so if you have any smart device, you may worry about this a little bit. So anytime you have anything internet connected, which is why making things internet connected is a little insane, you're opening yourself up to literally anyone who has access to the internet accessing your device, potentially. And if there are any vulnerabilities like this one, where they can just take control, they can run whatever code they want, that may not be what you want out of your device. Yeah.
So if someone gets control of your server, like that's root, how would you assume the server? Is there any way back to recover your server?
I mean, you could just like wipe, just reinstall everything. But there are techniques nowadays called advanced persistent threats where they will hide themselves. The malware will hide themselves, even I think even after reinstallations. These are probably more sophisticated state level attackers. But if in this particular attack that I showed here, where you just have a shell open, this is only going to be while the server's running. You could reboot your machine, and that shell's done. Just like Eustace. If you had if you've been on Eustace and you were ever like disconnected because the machine rebooted, yeah, that's enough, because this is just a process running. But you're still open to exploitation. But once they have a shell, they can do all sorts of sysadmin tests, like install their own software, install their own version of Apache or the web server, which gives them access, continues to give them backdoor access. So so basically, once you're sysadmin, once you're root, you have full control of that machine, at least of the operating system of that machine. Maybe not the hardware, but you have full control of that machine from the operating system point of view. So you can do whatever you want. And especially state-level actors, their goal is not necessarily to gain money or destruction, is to just sort of spy and stay present. So that's why there are these kits that they develop to maintain their presence on other machines secretly. But yeah, this is a big problem, software exploitation. And this small memory issue, this memory corruption issue, is the source of a lot of these over the past decades and related ones. Yeah.
Have you ever thought about implementing multi-factor authentication, like command line prompts and secure shells and things of that sort, just to combat this in a way?
I mean, you'd have to. You mean like modify the shell program itself?
Yeah, it'd be like crazy to do it like a base level.
I don't know if that's a way to solve it. I mean, at some point, if you're root, that means you can rewrite memory, you can rewrite the file system, so any authentication you have could presumably just be circumvented by the root user.
I also mean to get access into the root account.
Well, but if the web server is running as root, and then you can run arbitrary code, that's it, you're done. There are hardware approaches, the trusted computing base, trusted execution environments, that basically provide security from the operating system itself, sort of something under root, like because it's at the hardware level, and you could protect keys that way. But yeah, if you're, it's just your security model. So who do you trust? And it's like stealing somebody's key to their house. It's like, well, could you just add a better key to the house? Well, no, because you just steal the key, and now I can get into your house. Doesn't matter how sophisticated you could have this concrete steel door with this really fancy lock. If I take your key, it doesn't really matter, right? Because you were able to get into the house. You trust yourself. So if somebody's running as root here, and I can do whatever I want as root was already trusted, right? The sysadmins were trusted. There are other techniques for kind of compartmentalizing. Like you're probably not going to be able to do this exploit today, because there have been techniques to just like reduce the privileges of the web server, compartmentalize systems, provide multiple layers. You ever see people, they'll I hacked the CIA, and they put up a new web page. Their web page is not connected to anything sensitive. So there's other defense in depth and other design principles that mitigate these kinds of attacks these days. So that if this is just a web server, their secret stuff is not accessible from the web server. You hope. Okay, questions on the attack? So we have a pretty strong security program here. It's a master's in cybersecurity. Just give you another ad, and I think security is required. So security and computing. So take that, learn about CIA, confidentiality, integrity, availability, all the security principles. But all right, so let me show you how this attack works, because now that you've learned how functions are implemented in the compiler, you have at least some basis for understanding how and why this attack will work. There are a bunch of other steps in here so I'm not an expert in software exploitation. I just took somebody's blog, and there are exploitation tools out there. So I'm basically like a script kiddie doing this, because there's existing tools that I'm going to use that somebody else showed me how to use. So I'm not an expert in doing this, but I can at least demonstrate the attack for you, and kind of explain what's going on at the machine level and why this attack works. So this attack is going to use a different approach to get the shell code. So shell code is the precompiled exec shell. That's the precompiled syscall. It's called shell code to cool people, to the actual security people. They call it shell code. And so, this means that it needs to be specific to your machine, to your operating system. Now, the shell code in this exploit is going to be inserted in a different way into the program. So here we have our stack with the return address. But we're going to use the environment variables to get this in. This can work remotely as well. Web servers used to store environment variables. But you remember how, just to give you a quick, we didn't really talk about environment variables too much, but you remember when I had you use the user variable, I said something like COP for the remote server. You put something like this, right? The environment variables will replace that with the user variable. These are just like bash persistent variables. There's lots of them. Like your home directory is stored in an environment variable. Your current working directory is stored in an environment variable. And this is just a feature of bash. It's where also your path. We talked about path. So this is what stores the executable paths in the shell. So we're going to insert shell code into the path. And if you remember when we had these variations of exec, there was this environment variable that I just told you to make null. This is where this data gets put into the process. So bash has things like the path, the current user, and this gets, when bash runs a program, this gets copied into that program's address space. So just a feature of bash. Windows has these as well. There are Windows environment variables. And that's how we're going to get this code into memory, because when you call exec and give an environment variable, those environment variables are going to be stored in probably in a heap. It's going to be stored somewhere in memory. It's not going to be in the stack. It's going to be in the heap or the data segment somewhere. But these environment variables, they're going to be stored in memory. All right, that's all you really need to know for this attack. We're not going to, that's how we're going to get the shell code into the memory of the process. We're going to do it through an environment variable. Okay, so let's do the attack, and hopefully it'll work. So again, I'm not an expert at doing this. I went through this a couple times, so hopefully we'll get it working correctly. And I put this on GitHub as well if you want to try it out yourself. I set up a Docker image so you can do it safely on your machine. You have to turn off some other protections on your machine as well. So this kind of attack is probably very hard to pull off these days for most systems. But okay, so let me enter the virtual machine. All right, so now I'm in the virtual machine. Let me go to the code section here. And there are a bunch of tools that this blog post, really good blog post, kind of showed how to conduct this attack. So I've got this program here, this C program. Now let's go over what the C program does. So main gets called, and it calls this function vuln. Vuln declares a character buffer, a string of 80 characters. And then it very naively reads 400 bytes into that buffer. So this should all look familiar, right? You've seen the read system call. It's going to read 400 bytes into this buffer. Now, you wouldn't actually do something this naive, right? It would be something like a string copy where you don't know the length of the string ahead of time. You don't check for it. But this just illustrates, copying 400 bytes into an 80 byte buffer. Questions on that? Make sense? So you can hopefully see why this would cause a stack smash. Why this would smash the attack, because if I have an 80 character buffer here, and then I write 400 characters to it, I'm definitely going to overwrite the return address somewhere. All right, questions on the code so far? Questions on the setup? Yeah.
It goes all the way to 400, right? So
Yeah.
if it goes past the stack amount, what happens?
It's going to overwrite the return address, and then when the return instruction is called, it's going to try to branch to that overwritten value, whatever you've overwritten. And you see what I mean? So if I've and this is reading in bytes. So if I put the character A, then A is going to overwrite, like actually 8 A's are going to overwrite the return address.
Yeah, so it'll overwrite the RDP, the return, and then it'll keep going. But what's
Keep going.
over there?
That's the prior function calls. If you go high enough, you just get to the top of memory or some other part of memory. But it's going to overwrite. So because this is called by main. Main calls vuln. So vuln's return address is going to get blown away. Then main's going to be blown away, and then the caller of main, which is the C runtime, the start function. But the sort of main point here is that this return address gets overwritten when we do this. But yeah, I guess if you went far enough, you'd hit like the top of the memory space, or you'd eventually get like a write to a memory location you don't have access to, and then the hardware would stop you from doing that. Okay, so this is just a very naive program that will absolutely allow you to smash the stack. Okay, so I've got a debugging version of this so we can do breakpoints. I've got this function, I've got this input here that just has hundreds of A's in it, the letter A. And if I input this into my program, well, it stops at main. You can see it's already blown away so 41 is hex for A. This is the instruction pointer. So when I ran this program with just a whole bunch of A's as input, it overwrote, and A's is hex 41. It overwrote everything in my stack with just a sequence of the letter A, hex 41. And this IP, this is the instruction pointer. And so we ran this program, and it tried to jump back to main, tried to branch back to main. But instead, it's going to branch to hex 41, 41, 41, 41. Make sense? Everyone see why that happened? So I called vuln with just a bunch of A's. The letter A was put in here over and over and over. That's hex 41. And so the return address was overwritten with A. And so then when vuln tried to return, when it went to the next instruction to return, it branched to address 41, 41, 41, 41, 41. So this is why this is the saved RIP. It hasn't actually jumped there yet. I think that's where the break goes. But you can see that this is the return address that it's going to branch to. So if I were to run this function, if I were to just run this with that input, what do I call it, normal? Then I'm going to get a segfault. It's going to try to branch to address 41, 41, 41, 41. All right, questions on this? Questions on this or? Yeah.
That's from the phone call, right? Not the phone call.
That's caused by the phone call, because that's caused by this read. This read is what reads in 400 characters, up to 400 characters from the input, which was just a sequence of hex 41 or A's, and reads it in, smashing the stack, overwriting the return address. And then I think line 13 is just before it's about to return. So yeah, so it's it's going to be the point of the program right before we return. All right, questions on that? Does that make sense? So we've successfully smashed the attack. Now this is where the security experts really come in, where they know how to exploit this. Based on this blog post that I use, I've referenced it here. You can take a look yourself. They use this GDB plugin that helps you do exploitation. They have tools to help you exploit code. So it's going to do some fancy stuff that I don't fully understand, that I'm not an expert in. But what we're going to do first is try to figure out the distance between the variable and the return address. So you could probably do that kind of analytically, like looking at the code. But there's this trick they use where they put a kind of a pattern of bytes into memory, so that when you see those bytes here, it'll figure out the offset for you. So don't worry about too much how that works, but it has a technique where it'll tell you by just running the program, it'll tell you what the offset is between the variable you're using to smash and the return address. Because we need that, right? We need to know exactly where in these 400 bytes the return address is if we want to put our own value in there. Make sense? So we just need to know this offset. It's like RBP, right? We need to know the offset from this variable to the address. So if this is array 5, we need to find out that this is 6. So this is what this next sequence of instruction does. It uses this fancy trick. It creates this random appearing pattern of binary values. And when you run it, you can inspect the stack pointer to see what value of the pattern was in the stack at that point. So don't worry too much about this. What this means we can do is that, well, let me just make sure this protection is off. Yeah, so you can see it's always at the same, the return address, the return address is always at the same point in memory. There are protections called address space layout randomization that will move the program around in memory, so it's not always at a fixed address. That makes it harder for attackers to figure out where the return address is. But we're going to use this pattern to figure out the offset from our variable to the return address. So that's the offset I have. So I run this, and it tells me that I'm 104 bytes away. So this buff variable here, it's 80 characters. It's 104, 80 bytes. Characters are 1 byte. So it's 104 characters away from the return address. So if I write to buff 104 or buff 103, probably, I don't know which it is. It's offset 104. So buff 104, I know I'm overwriting the return address. Make sense? So this tells me that it's buff 104 is where the return address is. So with that information, I can specifically write so what I can do is I can make, or this is what the blog post did, I didn't do this, but what I can do is I can make 104 A's and then put another character. I guess this is B, right? 42. Put another character to overwrite the return address. So this will just prove that I've targeted the return address exactly. So it'll be 104 A's, then B, and then C's afterwards. And so now if I run the program and I see the letter B in my return address, I know I've targeted it correctly. So this will make that input. So just to show you, this is the input. You can see it's just 104 A's followed by a sequence of B's and then followed by C's. So this is the offset of the return address in my string, my buff string. And so I can show that it is that return address by running the program and showing you that the RIP pointer now has the value 42 instead of 41. So before, I just overrode everything with A's. Here I targeted just the return address to have the letter B in it. And with my debugger, I can show what the instruction pointer is. I can actually show what the return address was that it's trying to jump to and show that, yes, I indeed got B. Kind of make sense? So I'm just trying to specifically target overwriting the return address. Okay, so now here's where the shellcode comes in. So I just took this. So there's this website. Use it nicely. This is a website that has it's not up anymore. This was a website that hosts. Okay, it's still there. So this is a website that hosts a bunch of other binary sort of hacking materials, exploitation materials, and it has a whole bunch of precompiled shellcode for you. So I just downloaded this. I just got this shellcode. Now it's encoded. It's encoded in this. I don't know what this format is, like this encoding for Python, which will write out binary. Whoops, I'm still there. Oh, let me export this again. So I've taken the pwn environment variable and stored this unprintable binary code in it. Now, if I disassemble it, you can see what the sequence of assembly instructions is that is encoded by this shell code. So this binary blob here that you can't read with ASCII, if I disassemble it, this is the sequence of instructions that now this environment variable holds. It holds this precompiled snippet of machine code. And right here, this is where I've got my shell. This is where I've got my string to call the shell. So this is the, so unfortunately, I don't have the, probably should have shaved. There's a C program equivalent of this. Unfortunately, the address is no longer correct anymore. But I can show you this at least. The string bin shell, so this is how this is the path to the shell. This is its binary, this is what it looks like in hex, and that is somewhere in here. That string is in here, and this is a syscall to exec. So this is taking the string bin shell and then doing a syscall for exec. So that's what the shell code does. It's basically just exec bin shell. Okay, with me so far? So now I've got a program that will execute the shell, and I've put it in an environment variable. So it's here in the pwn variable. I can disassemble it to sort of prove to you that that environment variable does indeed contain this sequence of x86 assembly. And so now what I need to do is I need to get this into memory, and that will be in memory from bash. Bash will take the environment variables, put it into my program for me. And then in order to actually run this, I need to figure out what address it has in memory. So this is the state of my program when I run it with this environment variable. I run my program, I've got my stack up here, and somewhere in here is the environment variable pwn. Pwn contains my shellcode. So what I need to do is I need to figure out what address this is. So then, because I can overwrite the return address of vuln, if I know that address, I can overwrite the return address to be the address of the shellcode. Make sense? So there's another little utility that this nice blog poster wrote, which will give you the address of an environment variable in memory. And because other security protections are off, this will actually give me the address. So this is saying, this is a C program. You can see what it looks like if you're curious. But it will just get the environment variable. So this is how you get environment variables, and it'll basically compute the address for you. It'll as the actual hex address for you. So it tells me that this is the address that the pwn environment variables data is stored, and that is the address of the shellcode. So just like, let's see if this is the same address. Oh, no, it's a different address. So this is just like the code that this guy wrote to give 104 A's and then B for the return address. So instead, I'm going to give that address of the pwn shellcode as the address to overwrite. So now what's going to happen here? I'm going to run the program, vuln's going to run, I'm going to input this sequence of A's followed by the address of the pwn shellcode. And then when I run the vuln, when I run the program, vuln is going to read in this input, and then it's going to overwrite the return address with this address. As soon as the function returns, it's going to branch to this address, but that's my shellcode. So the shellcode is going to start running. The shellcode is going to call exec shell, and voila, I'll now have shell. Because what does exec do? You all remember what exec does? It replaces the current process's program with a new program. And so now this program that I was running, if it was a web server or something else, it's now just going to be running in the shell. And if I am running that program as root, well, now this attacker has a root shell open. So this could also be used for a local attack as well. If you have any programs, there's a security model in Unix that allows some programs have to run as root. So there's something called the set UID bit, which allows programs to run as root by users. But if they're safe, the user can't modify the program. So if it's a program that doesn't allow arbitrary execution, then it should be safe to do that. But if I have a vulnerability like this, then I can run as shell, because I can just can kind of hollow out that program, replace it with shell, and now I'm running that program as root. Okay, let's see if I can actually successfully do this. So, all right, so I've replaced it with the address that's supposed to be the address of this shell code. This will generate the code. So this is 104 A's followed by, non-printable address, that address of the shell code. And so normally now, let's see if this actually works first. So this is just passing that exploit code into my program. So it says no shell for you, but I'm running a shell right now. So let me run that again. Whoops. So this is that classic .c program that I was trying to exploit. So it says, prints this out, prints out put s, and then when it returns, it's actually going to branch to my shellcode because I put the exact address of the shellcode that I had in memory in the environment variable, and I use this exploit, the stash smashing attack, to replace the return address with that address. And now it's running exec shell. You can't really see anything because it's just the sh. It's not bash. It's the sh program. But I can prove to you that this is root. Who doesn't work here? I don't know why. But I can prove to you that this is root by touching a file, by creating a file that only root can create. Oh, no. Oh, okay, sorry. I forgot to. Okay, so one thing is I have to actually run this program as root. This program has to actually have this set UID bit to allow it to run as root, as many utilities do. So now when I do this, hopefully this should work. Only as root. Okay, so you can see that this only as root program was created by the root user. If I try to do that just as the user, so touch try as user, I get a permission denied because I'm not the root user. Excuse me. But by having this program that is allowed to run as root, because system utilities need to run as root, I can execute shell as the root user, replace this process which is running as root with the root user, and now I can do anything that root can do. And so you can see that these programs, or these files, have been written with the root permissions. All right, kind of makes sense? Questions on this? So, yeah, go ahead.
So, this is for the sake of, well, is there like a live example of this, like a video of, this is an example server running and this is how I exploited it sort of thing? Do those exist on the website you've shown us?
Probably, yeah. I would just go on YouTube. Probably they exist. You mean like live, more live than this? You mean like
as in like,
network?
Here's a server that's actively running programs are being used, and this is how.
So the problem is these days it's illegal to do this unless it's your own equipment.
Okay.
So if somebody's doing that, they're probably going to do it anonymously, or they'll do it on their own server. But you can certainly, I'm sure there. So I am not a security expert. I don't do this exploitation. This is not my job. I just use this as an illustration of the knowledge of how the compiler and the operating system work.
Gotcha.
But you can certainly find, go to watch DEF CON videos. That's a Black Hat. These are classic. So these are security conferences that have bleeding edge security exploits and security practices. So DEF CON is a really popular one. There's a local one here as well. Oh my God, I can't remember the name. B-Sides, I think it's called. But if you're really into security, join Hack UCF. They go over these. They have these tutorials. YouTube will definitely have people showing you these exploits on their own machines, hopefully. But yeah, you can definitely find this kind of. This thing is excites you. If this is interesting, hopefully it'll give you an appreciation for system software, operating systems, and compilers, because being able to do these kinds of attacks demands having detailed knowledge of how these systems work. But you also may just be interested in the security aspect, defending against it. And there's huge amounts of jobs openings for security. And this is kind of some of the classic software exploits. Now, this particular one is mostly defended against, this exact attack, There's kind of been an arms race between like defenses and attacks. And there's all sorts of other ways to get the shell code in, to get it running, to avoid having root. And then there are other kinds of exploits that don't depend on software exploits like this, different bugs or different security practices. So absolutely, there's tons of content out there about this, for sure. Other questions on this? Yeah.
So as the owner of the server that's been blocked, for example.
That I'm running?
No, just hypothetically.
Oh, yeah.
It just happened and you're doing on the server. And is the only way you would notice this is happening is it like you see a file that you didn't create? Is that the only way you
So there's an entire field of intrusion detection. This is its own area in security, intrusion detection, trying to find this happen. There's another arms race of trying to hide that you have your own process running. If you've ever had like a virus on your machine and they like renamed it to like, Windows or something like that to kind of hide it, there's all sorts of sophisticated techniques to try to hide themselves. And there's bugs in the kernel, the operating system itself, that have been exploited. Because when I run PS on here, this is still running, right? If I run PS, I can see that, let me see if I can see that root, something is running as root. Oops. So you can see that I've got root shell running, right? So you'd like immediately be like, well, okay, nobody should be running root shell. But if you can find a bug in the operating system implementation itself that allows you to kind of manipulate this process table or hide it somehow, or you could even change the PS program, right? Because now that I'm root, I can change anything on the file system, including the PS binary. I could recompile a new version of PS that will just like hide that. So that's a very hard problem. There's a whole area. There's tons of companies that do this professionally, intrusion detection, and it's a very hard problem. But yeah, other questions on this? Yeah.
They also recently heard that like some portions of like cybersecurity departments in companies have started becoming automated because the company will actually track what's in with repeated processes.
Yeah, automated vulnerability detection, that's a huge area right now, is using AI techniques, statistical techniques, other automation to automate detection and malware detection, for sure. Yeah, that's a huge area of research. Also an area of research, there are some faculty working on this now. Let me know if you're interested in that. Join HackUCF if you want to learn more about this. Let me know if you want any other resource, and have a good one.
Curiosity, who did you end up talking to implement this in class, or is